So today we're going to be looking at first order homogeneous differential equations. Okay, so first order, by the way, means that there is only dy dx and is not d2y dx squared or anything like that. Homogeneous basically means that the differential equation can be put into this form, and you might think, oh well, yippee, I've never seen a differential equation in that form. In actual fact you have, and many differential equations, as we're just about to see, can be put in this form and then they can be solved by this method. So let's just have a look at some differential equations which are probably more familiar and put them into this form. So this one here, we've got x squared y dy dx add 4x cubed add y cubed equals 0. Well, we can change that. We can put that as a dy dx times x squared y equals minus 4x cubed minus y cubed, and then when we divide by xy squared we get dy dx equals minus 4x cubed minus y cubed over x squared y, which we can then rewrite as minus 4x over y minus y over x squared. And there we have it in the form dy dx equals f of y over x. Let's have a look at this second one here. Again, this can be put in that form. Let's just bring that x down there. So we have that as dy dx equals x squared add y squared over 2x squared, which we can write as, dividing by the bottom, a half add a half y over x squared. So again, that one can be written in the form dy dx equals f of y over x. Let's have a look at this third one. At first glance, this one looks like it can't, but log x minus log y is equal to log x over y. So that can be written as log x over y, and then all we need to do is bring this y down, and we get dy dx equals y over x log x over y, which again is now written in the form f of y over x. Now occasionally you get them written in, you see them in this form here. Well, basically again this one here is a homogeneous, so let's just move the dy onto the other side. So that'd be 2xy dy equals x squared add y squared dx, and then move the dx across. We got dy dx equals x squared add y squared over 2xy, and that we can rewrite as half x over y add y over x, which again is now in the correct form. And finally, let's just have a look at this fifth one here, x cubed y cubed dy. This is another way that they sometimes write it, with the dy on one side and the dx on the other. Again, we can just rewrite that as bring the dx over there and bring that over here, equals x to the 5 add y to the 5 over x cubed y squared, which can be rewritten as x over y squared add y over x cubed, which again is in the right form. So you can see that in actual fact many differential equations can be solved using this method. Now, just some out of interest, you might think, well, how do I know if a differential equation can be put in this form? As a rule of thumb, it is only a rule of thumb, if you look at all of the terms, that one, if you then you add up the exponents, that one adds up to 3, that adds up to 3, that adds up to 3. When all of them have the same degree, i.e. degree of whatever it is, then you can tend to put it into this form. Here, that one's degree 2, and if we move the x across there, that's degree 2. So this one can be put in as well. That one's slightly different. This fourth one here, degree 2, and that's x to the 1, y to 1, degree 2. And here, we got 3 plus 2 is 5, 5, and 5. So whenever they're like that, you can tend to use this. Okay, so let's have a look at what we're going to do. Now, obviously, the ideal, what we're aiming for, the sort of the holy grail of differential equations, if you like, is we want to have, when we have dy dx equals a function of x and y, what we want to be able to do is separate that into g of x, h of y, i.e. separating the variables, and then what we can do, once we've separated those variables, we would have dy over h of y equals dx times g of x, and then we can just integrate those two, and that's integration by separation of variables. But we can't do that with any of these. It's impossible to put it in that form. So what we do is we use a substitution, and the substitution we're going to use is v of x equals y over x. Okay, and basically that means that will be y equals vx. So therefore dy dx, just differentiating this by the product rule, is going to give us v times 1 add x times dv dx. Okay, so we know that from the beginning we know that dy dx equals f of y over x. That's what we had right at the beginning. That's the definition of the homogeneous equation. So we can therefore write that, therefore, v add, just moving this down here, x dv dx equals f of, well, we know that y over x is v, because that's the substitution we're using. And then what we can do with this over here is we can say that x dv dx equals f of v minus v, and so therefore dv over f of v minus v equals dx over x, and hey presto, we now have separated the variables by using this substitution. And that's what you'll find whenever you use this substitution on a homogeneous equation. You will find that we end up with something where we can separate the variables, and then we can integrate, and then we can put back y equals x into v and solve. Okay, so one other thing is that you will tend to find almost always that on the right hand side you have the integral of dx over x, and the integral of dx over x of course is log x plus c. You will find that all the time on these types of questions. So let's do a question here. So let's have a look. So we've got to solve xy dy dx add 3x squared add y squared equals 0, given the initial condition that y of 1 equals 1. Now just looking, we have xy, well that's x to the 1, y to the 1, that's 2, 3x squared and y squared. Okay, well they're all add up to 2, they're all of degree 2. So this looks like the sort of differential equation that can be solved using the substitution. And given that it is on a video about the substitution, we can be doubly sure that it works. So let's have a look. So basically, let's just put it in the form. So if we divide everything by x squared, we get y over x dy dx add 3 add y over x squared equals 0. All I've done is I've just divided by x squared, and then hey presto, we have it in the form of dy dx equals f of y over x. And so now we can use our substitution. V of x equals y over x, i.e., as we've just discussed, y equals vx, i.e. dy dx equals v add x dv dx, as I've just done just above. Okay, so we're going to use that. Now we're going to put this and the substitution into here, into this one here, and let's see what we get. So basically, y over x, we know that's v, so that'd be v. We know that dy dx is v plus x dv dx, and then plus 3 plus y over x squared, which is this bit, well, by the substitution, that is v squared, equals 0. Okay, so let's now just, that's v squared add vx dv dx, add 3 add v squared equals 0, i.e. vx dv dx equals minus 3 minus 2v squared. So we have that v dv, moving this down here and then the x across there, over minus 3 minus 2v squared equals dx over x. All I've done is I've taken the x's onto this side and the v's onto that side. And now we have our separation of variables, and so we can integrate both sides, which was the whole point of the thing. Now let's have a look at let's have a look at this one first. Well, clearly we have a v squared here and we have a v here, so we're going to, this is going to be some form of the integral of this by using the chain rule. So let's just have a quick look. V over minus 3 minus 2v squared, we want the integral of that. Well, what we're going to have to do is take the minus out and then multiply by 4 1/4, and then the differential of this bottom bit will be 4v, which is the top bit, and so therefore the integral of that there is minus 1/4 log of 2v squared add 3 equals, and the integral of this, as I've said earlier, is log x add a constant. Now, constant of integration. Now, normally on these questions, I tend to put the constant as log of another constant. Log of a constant is still a constant, so log of x add the log of some other constant, whatever, let's call it a, and then we can rewrite that as log of x a, where a we know is a constant. Okay, so basically now we have the log of 2v squared add 2v squared, that's squared, that is 2v squared add 3 to the minus a quarter equals log of ax, and so therefore we have 2v squared add 3 to the minus a quarter equals ax, and therefore if we multiply this by to the power of 4 and this to the power of 4, we have 1 over 2v squared add 3 equals a to the 4 x to the 4, and again a to the 4 is another constant, let's call it d x to the 4. Okay, so we're almost there now. All we've got to do, let's flip it the other way round. So we have therefore 2v squared add 3 equals, and again let's call it a different constant now, f over x to the 4. All I've done is I've flipped this, and again don't get confused by the constant. We don't know what the constant is, so if d is the constant, well 1 over d is another constant. We just call it something different. We're going to find the constant once we put the initial condition in a minute. Okay, so now what we can do is we can re-input y over x instead of the v squared, which was our original substitution. So we have 2 y over x squared add 3 equals f over x to the 4, where f is a constant to be found, remember, i.e. we have 2y squared add 3x squared equals f over x squared, i.e. y squared equals a half times by f over x squared minus 3x squared. Now we have the initial condition up here that when x is 1, y is 1, and that's what will enable us to find this constant. Now it doesn't matter how you've used this constant, you will get the same value. So let's put y equals 1 and x equals 1 in here. That equals 1 equals a half times f over 1 minus 3, i.e. f equals 5, and so therefore we know that the solution to this equation is y squared equals a half 5 over x squared minus 3x squared, i.e. y equals plus or minus the square root of, the square root of a half 5 over x squared minus 3x squared. That's the neatest square root sign I've ever written. And there is the answer to the question. So you can see basically what we do is we basically just follow the same pattern. We have to first of all put our equation into the form y over x, and we've already discussed that. Then we use the substitution v equals y over x, and then we input dy dx and v to get an equation where we can separate the variables. This will always happen. We can separate the variables into v and x. We solve that. We stick back y over x instead of v, and then if there is an initial condition, we input that to find our constant, and then we have our solution here. Okay, well I hope you found that useful. If you did, please like the video and subscribe to the GRE Academy YouTube channel. Thank you very much.